I'm Ionela Voinescu. I am part of the power and performance management team in the architecture group in ARM. I think over the years you might have seen some bits of work from me on the scheduler, on CPU freak thermal. Nowadays, I usually work on OSPM to firmware interfaces, so usually focused on power and performance management. This is what I'm bringing up today. I pompously call this an architecture RFC for platform-specific resource prioritization, but it's basically about integrating two new firmware interfaces, the functionality from CPPC resource priority registers and SCMI prioritization into the Linux QoS infrastructure. So I'll briefly go over the introduction and then the details of how this functionality fits into the Linux QoS landscapes. And I was hoping to have a discussion on the approaches for integrating this functionality so it's useful for people, at least for most people. So I think that the background of this is, so on most systems today, usually we have a system control processor, and from power and performance management point of view, that system control processor has the responsibility of evaluating constraints. So it will look at power limitation. For example, you have limitations of your power supply, and it will look at thermal limitations as well, so constraints as a result of environmental conditions. And as a result of that, it will do some sort of resource partitioning. It will split the resources between the power resources between the devices of the system. I'll mostly be focusing on compute. That is, whenever there is an excess of power, usually that goes to devices as a performance boost. Whenever there are some constraints, usually that goes into performance capping for devices. And I'll be referring mostly to CPUs. Up until recently, this functionality was hidden from the OS. You could observe it via counters, but the OS never had the possibility of actually configuring or where that excess of power or where the constraints will go. So the new interfaces bring the possibility for the OSPM to mention what are the most important CPUs for that partition to be done in a more informed way to the needs of the application. So the main question is, so having that in mind, having the possibility of routing, let's say, or the possibility of providing priorities when it comes to resource distribution, how do we route that information from user space, from the user needs to the user intent through the QoS landscape of Linux into hardware prioritization? And I thought it would be nice to have a visual of where this would fit into the QoS landscape. It's not, there are lots of caveats in here, and it's probably not a very good description, but I wanted to sort it from basically high-level user intent, and that usually comes, let's say, from Android. Usually Android has quite abstract QoS hint. So you have something like the functionality of the power HAL that usually can react to something that's happening on device, either touch or app start, and it will give you a performance boost, or you can have configuration of certain modes that are suitable to the application. So you can have gaming, and you can configure sustained performance or low use, and you have low power modes. So all of those usually are quite high level and just mention user intent. That usually gets translated. So for example, I think the server world usually starts at the second layer, gets translated into more specific scheduling policy, not necessarily configuring directly the hardware, just configuring how the scheduler uses that hardware. So you can have, of course, per task policies, C groups. That is, you can configure how much time a certain task gets on CPUs or what use of CPU it has. You can restrict certain work on little CPUs, for example, work that is not important. And then we go to a level where we get a bit closer to actual hardware control, or at least knobs that have more impact in how you configure hardware. So usually UCLAM, for example, has the possibility of inflating the task in order for it to get better frequency via DVFS or get placed on bigger CPUs. And the same thing for CPU freq limitation. You can configure a min and max, so you get more quality of service for your applications. Then when we get closer to hardware, we have more hardware partitioning, and you can partition, for example, your power. You can specify via the power cap interface some power restrictions for your devices for a limited amount of time, or you can partition your caches and your memory bandwidth via the REST control interface. There is one interface for the interconnect. I think it can configure latency and bandwidth, but there's no interface through which one can configure these sort of the excess of compute, the excess of power that could be distributed as a boost in performance, or whatever power budget is available in certain scenarios. I think this is where the new interfaces fit, the ACPI CPPC and the SCMI QoS interface. There is already a solution from Intel, which is the SST-CP core power, so Intel Speed Select core power, that has a similar functionality, and it's supported via custom tool. I think it's useful to also know that each of these act at different target scopes. So some of them act as task level, processor level, domain, or system, and there are usually complications associated with aggregating per task information into per domain or device information. So seeing where those fit, I think sort of the details that are worth noting about these two new interfaces is what they actually bring. So what are we actually getting on the application side whenever we prioritize resources in such a way? So the CPPC interface provides you with registers in which you can configure priorities from 0 to a priority count, 0 being the highest priority. So you can configure your resources, which can be processor boost, processor throttle, caches, and memory bandwidth. You can configure the amount of basically resources that are prioritized on those devices, and these are per logical CPUs. The way that this is distributed, I'm exemplifying here the processor boost and processor throttle. So we have the CPPC performance scale that is ranging from the lowest performance to the highest performance, with nominal performance being the performance you typically get under typical conditions. And there is the possibility in CPPC to modify that nominal performance in order to increase the power budget available for boost. So, for example, what one would do is lower your nominal performance in order to free up power budget in order for this to be distributed as boost for the most important tasks in the system. Additionally, for throttle, you can decide who gets throttled first in thermal conditions. I think in the past, all of this functionality was static. That is, the platform had its own policy. It would, for example, in thermal conditions, it would throttle the big CPUs first because they were more expensive power-wise, and it would keep the little CPUs unthrottled because they were more efficient that way. But that's not necessarily aligned with the needs of the applications. So this allows you to direct either boost or decide who gets throttled last in certain conditions. And
excuse me?
Yes.
So this L2 cache, L3 cache, and memory bandwidth categorized into this computer priority or using the previous MPAN?
They are, I mean, the interfaces themselves, I categorize them myself as compute. These parts are, so the interface provides you the possibility of configuring priorities for these resources. But the interface to actually configure those priorities is not yet defined. That is probably, so this collides with the MPAN functionality, and the configuration of this could go via REST control as MPAN does. But this is a different interface that basically does the same thing. So this more configures priorities to these resources. MPAM, I think, does more of a distribution, that a more exact distribution of caches and memory. This only says who's more important in accessing these resources, whether one CPU or another CPU. So the priorities here are from 0 to n, with 0 being higher priority, and this is an index mode. The policy is usually platform specific. So probably one implementation could be that your highest priority CPU will get all the resources up until a max, and then it will sort of trickle down to the lower priority resources. So it's not very high granularity. It's just saying who's more important than another, where MPAM and sort of the rest control interface is more detailed. Oh, yes.
ACPI specification gives a little bit different picture of highest performance, nominal performance, guaranteed performance.
Okay, and it's not complete, but yeah.
Okay.
I mean, mine is not complete.
So guaranteed performance is given as a range, and also there is non-linear plot
yes.
performance in the middle somewhere.
Exactly. So this is just a visual, because the important part for this is usually the fact that you can configure nominal performance in order to free up that boost. So usually boost. So you have a nominal performance being under typical conditions. So let's say all CPUs can maintain nominal performance when all of the CPUs in a voltage domain are active. So this means that you can lower that nominal performance so you can afford to have boost available on certain CPUs, even if they don't actually go idle. So even if you don't have a fully loaded system, or even if you have a fully loaded system.
One question?
Yeah.
So could you explain a bit more the difference between the guaranteed performance and the nominal performance?
I think the guaranteed performance, it's a bit tricky to interpret. So it's probably explained in ACPI, but I think it's always been a bit difficult to interpret. It's supposed to be the performance you can maintain under heavy constraints. That is, for example, you could choose lowest performance or lowest nonlinear performance for that device, for that CPU, but guaranteed is supposed to be available to you even if you're under thermal constraints and so on. But I think that's usually quite platform specific, and nobody can agree exactly what it means. And usually the guaranteed is the lowest. That is, we can only guarantee a certain level of performance for all conditions. Yes.
Specification says that if you don't guarantee performance is first of all optional.
Yes.
You are not required to provide this register. Now, if you don't, then the nominal performance is all your guaranteed performance as well.
All right.
If you do, then the guaranteed performance is supposed to be in the range between nominal and lowest.
Yes.
And then there are two cases in which one case is when the register is read only, and that gives you the performance that is sustainable. The thermal conditions are not mentioned in the section as far as I can remember right now. But this can also be on some platforms that can also be read write, if I remember correctly, in which case you say the OSPM can say what performance should be provided. But again, this is a new section in the specification, and I don't exactly remember all of it right now. But yeah, that's basically what's there. So it's way more complicated than
yes. Yeah, definitely. So this is not necessarily to describe CPPC, just to say what are the additions to the existing CPPC. That is the prioritization of this
part that actually the guaranteed performance has been there for forever.
Yes.
But the part that is new is this package with the priority registers. So,
And the fact that you can now modify nominal performance, which plays into this.
yeah, well, you can. This is a register.
Yes, exactly. So it's
If it is not, because it might not, it may just be a number.
yes.
In the case. So yeah.
So SCMI QoS is very similar from that throttle and boost functionality point of view. So SCMI is an ARM interface for system control, and it has a lot of focus on power and performance management. QoS is an addition to the performance protocol. So basically the performance protocol is similar to CPPC, just describes and controls your performance. The SCMI QoS additions basically bring relative and weighted priority for boost, throttle, and combine. So basically you can have a CPPC indexes to access boost and throttle, or you can actually have weights and say how much of that boost is given to one device versus another. What's missing here is the access to memory bandwidth and to caches, because that's handled by MPAM on ARM. And it has two additions sort of compared to CPPC. And those additions are EDP, which is similar to ACPI's EPP. That is a value that tells you whether you want to steer more towards performance or power, and an operational mode, which is something platform specific to target certain pre-baked functionality. There is a structural difference as well. So CPPC is per logical processor, while SCMI actually divides QoS into domains. So you can group certain devices into a certain domain, and you can have from lower granularity per processor priorities to higher level per group of devices priority when compared to one another. So you always, from point of view of priority, you always compare your devices, your domains that are under the same parent. And the reason for this is that in certain situations you might want to have a certain type of priority when it comes to boost, and when it comes to sort of thermal scenarios, you might want to prioritize, for example, your entire compute subsystem versus your GPU, and not necessarily prioritize each CPU in part, which you might want to do in for boost conditions.
So boost and throttle here are referred to frequency?
Yes,
only?
Exactly.
Okay.
So that's the so it might not actually, it's platform specific. So I think in most cases it will be boost, but I imagine that it can be something specific to the processor as well in order to give extra performance, because frequency is not always the best path to actually get extra.
So it does not include cache?
No, it does not. So SCMI QoS does not, because there's MPAM available. That is, there is another ARM feature that allows distribution of caches.
So SCMI performance management on CPU devices as well as
Yes,
CPUs.
exactly. So the domains can contain any devices, while CPPC only handles CPUs, of course.
You said that the priority is about you can set the frequency. I mean, you can select whether a CPU is supposed to receive a higher frequency or not, or more memory bandwidth or not. There has been some discussion saying that sometimes it's not useful to raise the frequency.
Exactly.
It's an issue if you have only one register for two different.
So I'm not sure if I understand you correctly, but of course it must not. That is it's the responsibility of the platform to make sure that those configurations do not conflict. In the sense that you can say this CPU has high priority, so it might get a boosted frequency, but on the other hand, you might have some memory limitation that does not take any benefits. You're not getting extra performance out of the boost that you allow for the CPU. And it's the responsibility of your kernel platform configuration to make sure that.
Right now, if you ask for more boost, you get more memory bandwidth.
No, so this is only for performance. That is for the resources of the CPU, with the exception of caches. So no, SCMI QoS does not work at all with memory, bandwidth, and cache accesses.
So I was thinking about the previous slide.
Okay.
So right now with this interface,
Mhm.
you ask for, so if you set 1, for instance,
Yep.
you will get a higher frequency on more memory bandwidth at the same time. It's not possible to distinguish the two.
No, you can. So you will set priorities for each of these resources.
Okay.
So it's not, you basically get one register for different resource types, or for each of the resource types.
Am I wrong, or you said something that SCMI performance protocol is similar to CPPC?
It's just in spirit, in the sense that it's
spirit,
exactly,
they
no,
very different things.
Agreed. It's just in spirit they both deal with performance control. So exposure, performance capabilities, and performance control.
We might have a question from remote.
Okay.
Alex?
Yeah, so is there anything in SCMI QoS that makes the nesting of the domains explicit? Or you just have to know that's how they're nested? Like I see like domain 9 is within domain B, or?
So each of the domains will have a parent for QoS purposes. So it is explicit and discoverable.
Ah, okay, thanks.
Welcome.
I have a question. So in the code architecture, what's the current QoS behave with current like CPU frequency and tuning, and for cache or memory bandwidth, it is about the MPAM specific tuning. Why have SCMI QoS separated system level tuning? Is it if the SCMI is the same as CMI, it is only the interface to interpret the kernel hint to the firmware, right? So that means you want the firmware to decide the CPU boost or not, the memory to have higher priority or not. But actually the specific control already in the kernel end do have such kind of detailed control. Like MPAM also have priority attribute, right? And the isolation like CPPM attribute, more detailed control is already opened from the kernel interface. So why SCMI QoS then?
Okay, so I think so the reason is MPAM, it's ARM specific. So the ACPI CPPC interface might be implemented by non-ARM platforms. So you might not have your memory partitioning either provided by MPAM, or I think Intel has a solution as well, and we have solutions as well for that. So this is more generic for scenarios when you don't have something more specific. I suppose you can use CPPC prioritization. And it's the boost and throttle functionality. I don't think there is any other facilities but this, that is for you to control your platform policy when it comes to allocated boost and throttle. There are some facilities that allow you to specify from the kernel whether or not you want a level of performance between your nominal performance and your highest performance, but it does not. It's not guaranteed, first of all, and it's not possible to specify where that would go. You might ask for it, you might not get it, but it's not possible to direct it. So these two interfaces, first of all, provide this new functionality for boost and throttle, and for memory, I think it's just for systems that don't have any other facilities.
It's important to understand the difference, right? So if you look at those L2, L3 memory bandwidth parameters in CPPC, right? In ARM, right? We are potentially not going to use it at all. It's all going to go rest control, right? Now, who added? Why were these added? Is a question you might ask, and unfortunately, we at ARM do not know the answer to that question. So probably for another architecture or another operating system entirely, right? Because I don't think the proposal came from Linux, at least for adding number 3, number 4, and number 5 over there, right? So it's unknown who added number 3, number 4, number 5, and why, or what are the motivations over there, right? But certainly for ARM, right, we think rest control is the right interface rather than this for the cache and memory related parameters.
Yeah, even for the first one, processor boost or throttle.
They are related to CPU FREC,
Yeah.
right?
Already super.
Right, so these two are related to CPU FREC, and in CPU FREC you can control frequency, right?
Yeah.
Between the CPUs, but when you're putting the CPUs to certain frequencies, right? And the firmware does not have the thermal or other headrooms to provide you that frequency, the firmware is going to throttle, right? And it often throttles randomly. But now you can tell it which
Like
one.
another thermal trying to throttle it from the firmware.
No, exactly. Firmware always has thermals inside, so you can tell it exactly if you're under thermal pressure. I want you to throttle this. Please do not throttle my high priority cores because today it's a random hit, right? It just hits the cores in whatever order it seems fit.
Yeah, I think it's not. I mean, it probably has some logic. That is the split that the firmware does. It's unknown to the operating system, and it might not fit all scenarios. So you might have, for example, the boost distributed equally between CPUs, while you might want all of that boost to go to a single CPU that you consider important. So it's probably logical. It's just it might not fit all scenarios, and you might want to control it.
Your cache is usually inside the performance domain. So
yeah, so
you
that
can-
is the
you can
L2.
play with the boundaries with the performance. I mean, what's happened if we ask to boost the performance domain, which include your cache compared to this?
No, these are not cache performances. This is cache
On
allocation.
the
Exactly.
SCMI QoS side, I mean, you say you don't play with the memory bandwidth or the L2 cache bandwidth, but in reality, your cache has a performance level which can be scaled with the SCMI performance.
Yeah, there will be an impact.
There's an implicit because it's a clock, it's the same clock sometimes, right? So there's an implicit hit. So even if you will do CPU prep,
No, I mean, it's not planned in your firmware to balance the fact that depending of the rest, there is no connection between what is set in MPAM with the rest control and what is then set on the SCMI or SCMI performance domain.
I think that's the whole discussion because today there is nothing in the minutes to set CPU priorities at all.
Okay, I'll get to that in 20 seconds. Oh, sorry.
Just one clarification. This assumes that the hardware firmware is scaling frequency on CPUs, or is it only when you are thermally constrained?
So it will have policies that happen even under unconstrained scenarios. That is, usually, let's say your power supply is never built to, or in most cases, is not built to support your maximum frequency, your highest frequency, your maximum frequency on all of your CPUs. So I don't know. You can consider this a constrained scenario. That is, you're under the limitations of your power supply. It's not necessarily thermally constrained. It's just you have a power budget that then you distribute between your CPUs in the same voltage domain.
Okay, so the OS in this case does not request for a specific operating point, or does
it does. So the OS will request a specific operating point. It does not know it will have that boost available and how that boost is distributed. So when it is available, you could distribute it equally, and more or less each of the CPUs could have an extra 20%, or you can sort of distribute. You have to have per CPU DVFF, of course, and you can distribute it only to a single CPU. So it depends on the platform policy. So it's not necessarily thermally constrained. It can happen in the general functionality of the device. So I've added this as an overview of both of the features and with added information for the existing Intel solution. When it comes to the differences in target scope, the ACPI CPPC targets logical processors, while SCMI works more generically at domain level, which can be different groups of devices or single devices. And as far as I know, the SSTCP interfunctionality functions at core levels. Basically, I think they move those cores into classes of service, and the index of that class of service determines priority, or they can configure weights as well. So the functionality when it comes to prioritization boost and throttle already exists for Intel as well. Equally, it does not handle any memory or caches and memory bandwidth partitioning.
Well, so this is technically part of resource control.
Exactly. So I think it is as for ARM.
The same interface is used for that and for cache partitioning.
Exactly. Yeah, I think from that point of view, only CPPC has the addition of handling caches and memory, and Intel and ARM have other features for this functionality. I think what's worth noting is that they're not all of them the same in the type of priority you specify. So a type of priority could be an index, the order in which the resources are distributed. That is power resources in most cases for most of them. Or it can be a weight. You can say by how much one CPU can get more power to increase its performance versus another. And I think this is the part that's up for discussion. Given all of these features, I think the question is, how can we integrate this in such a way that we provide these facilities to user space, kernel space, in order so it can configure the hardware, having more knowledge about the application needs. And I thought it was useful to basically consider this on a spectrum from what sometimes happens in the sort of QoS infrastructure. That is, you have one side of the spectrum that is highly fragmented and heavy on user space access. So you can have either custom tools or you can have specific CSFS interfaces, or moving to the other side of the spectrum in which you don't expose this to user space, but you infer the priorities that your devices, your CPUs will get based on the requests of each task specifically. And in the middle, you can have sort of variations of this going from either sort of more unified solutions. Maybe you expose a subset of your features in a unified CSFS interface, or you reuse existing interfaces, or you still expose the possibility of the user to configure these priorities, but that is per task priorities, and you don't necessarily infer it at kernel level. So I put this here just for us to see the spectrum of possibilities and just to gauge where interest sort of might land.
So first of all, CPU or I particularly like the idea of the task level interface. Rest control is already used. So there are a couple of things here. So rest control is already used for similar purposes. Maybe not exactly the same because that's not the priority.
Rest control is per task.
It's well, not exactly because they.
So we can go sort of through all the options and see the pros and cons. So more or less we can discuss each of them and see which one would sort of be more suitable.
Maybe one question.
Yeah.
How efficient is the access to this interface? I mean, it's 1 millisecond per when you are setting, or 1 microsecond, or 1 nanosecond?
So both the SCMI and the ACPI functionality can have different types of transport. That is, you can have system memory, which is very fast, or you can have PCC and mailbox, which is not. So it will still be platform specific. And I think any integration with a kernel and sort of scheduler would actually require fast access.
Yeah.
So I split a bit the.
Not only fast access, but also fast reaction time.
Yes, exactly.
There's a difference. You can ask for a DVFS change and then have it only 10 milliseconds later take effect. I mean, that's just
Yeah, I think so. Looking a bit at what you might get with different options, I've sort of sorted them in this way. And I think that goes under dynamic control in the sense that you get per task priorities, you aggregate them in some sort of per device, per CPU priorities and send them to the device. But if the device reacts too slowly, you more or less, the world has changed beneath you by the time you've actually sort of received what you requested. So it does require fast access from a single platform. And I think that's one, let's say, argument against maybe a per task solution,
So
if that's not suitable.
thing I would like is to start with maybe an idea how this use case that is going to be addressed with this. Because obviously that there is no use case, then we basically consider all of that. But
so there will be a use case, right? So in the mobile phone, in limited
fine.
budget,
What is it?
Gaming, and you have GPU, and then you have plenty of CPUs, and then if you prioritize the one which is running the main gaming thread.
Yeah, okay, so what I'm saying is I would like to know how this is going to be used by middleware, for example, to achieve the goal that you are, because
Yes, I understand.
yeah,
So
because the interface will depend on that, right? So
right.
Yeah,
But that's
how this is going to be used.
Yeah,
Like,
so I agree.
in
Rafa.
practice.
So there is this use case in that power budget that you have, and then there's a heavy load using also the GPU. And then for the CPUs, there is not that much of the power budget.
I think there are generic use cases in which this sort of makes logical sense, in the sense that, for example, you're thermally constrained and your default platform policy is to give more resources to your little CPUs because they're more efficient. But let's say you're running an application that has high performance requirements for a single thread. It is better for you to be able to configure the distribution of those resources in constraint scenarios to go to the thread that needs it. So that's more or less a generic.
Yeah, so my question basically goes into the direction of who decides which thread, and how that decision is going to be expressed.
Exactly.
Because that is a key factor here. Yeah.
It's not going to be probably the kernel itself. It has to be something like a middleware.
Right, so there needs to be a kernel interface for it to express its preferences. So that now the question is, how it is going to be used, because basically there are two ways. You can think about two interfaces, two types of interfaces. One interface is an admin interface. We have an entity admin or something that plays the role of an admin, and it will set arbitrarily things for some way of figuring out what is appropriate and then set things.
I think this is quite common in the server world, in which basically you pin your task, you partition your task already.
REST control is an interface like that.
Yeah, so that means it would be one of the, let's say, SysFS interfaces, either more unified or fragmented.
More or less. The other type is when tasks can specify their preferences, in which case it is way different.
Yes.
Because it has to allow a task to somehow interact with the kernel. And that would be a different type of interface.
So I suppose, of course, the solution can be a combination of these, because in this sort of spectrum, some interfaces are more usable for some markets. That is scenarios where you have an orchestrator that knows the main purpose of the platform, you can pre-configure it, and that configuration is stable for a longer period of time. While the other part of the spectrum is something that's more suitable, let's say, for mobile, which is a more per task interface. And I suppose a solution that, there could be a combined solution, that is that we can have, I suppose, a separate SysFS interface or something similar with sort of per task interface.
Maybe the middleware library that QoS was proposing, in which the application requires a level of service, and then the idea was that it was, I don't know, interactive, etc. And then the library will translate what the application
But
wants.
I think we still need something that conveys that to the kernel. That is either an addition to basically
that
sets
will be the library,
attributes.
right? That translates whatever the application wants it to.
Exactly. I don't think this will be configured by an, let's say, unauthorized user. It will be done by some middleware, some sort of daemon that manages the platform.
Yeah, but the application will say, I want.
Yeah, exactly.
I want I want the foreground QoS.
Okay.
And then the library will go and set those parameters, whatever.
But that will be something that doesn't exist today. That is for us to either, I don't know, have some C group extension or something like that. Should that was.
Yeah, a library that does that.
So I agree.
Have an internal interface.
Yeah.
Functions in that do these.
Okay, so it's not up to me.
Well, yeah, but that's my request. If we're going to have any sort of dynamic usage, nice if we don't bake it in, but we just make it usable by modules. With Android, we can have an upstream one.
But
they don't necessarily use the same.
So you wouldn't expose, it would be basically the last solution. You wouldn't expose anything to user space. It will be something that's internal.
No.
Okay.
It's kind of a privileged actor in the kernel.
Okay. But you still need something based on which you infer the CPU priorities, in the sense that, do you want that to be provided directly by a user space, that is, let's say, something added to shared attributes or something added to C groups, or do you want to infer it based on other hints that now the kernel gets, like sort of CPU weights or uclam min and so on? So would you want it exposed to user space or inferred?
Personally, all except through module.
Okay. But it's not very generic. That is, it wouldn't work in all.
Do anything unboxed.
No.
Have one upstream that exposes the SysFS interface.
And then another client just for the in-kernel interface.
We might not ship that in an Android device.
So actually the trade-off, it says the task of following QoS partitioning.
Yes.
That is what current resource control already does.
That is for memory, for the rest control, the resource control interface for memory partitioning. You're saying that that task following behavior, that's what it already does.
Yeah, it's already have the task of following.
So yeah, I think this is more about, I agree that memory is handled by rest control, so it's already covered. The part that it is not covered is that availability of performance boost whenever you are constrained, either by power limitation or thermal limitation. So the question is, how do we handle that part? Because I agree, everything, I mean, the rest is handled by rest control.
So for Intel, we have the SysFS turbo flag thingy.
Yes.
It should probably affect CPU capacity slightly, but it doesn't.
It does not.
The turbo flag, we have the turbo flag in SysFS somewhere, right? We can disable turbo.
Yes. CPPC has the same thing. It has a flag for boost, but you don't configure who gets the boost, right? You configure if it's enabled or not. That is, if platforms can access, that is, if platforms can ask for boost frequencies, but you don't control where it goes. So it's still the platform, that is, the platform policy is still hidden in the platform and you can't choose.
Is the turbo flag for CPU or just global? I forget.
It's global, and I don't think it makes sense in actually.
So I occasionally turn it off to make sure the benchmarks are more stable. Depends a bit on the microarchitecture whether or not this matters.
The difference between
turbo and not turbo with AWT enabled is that it will artificially limit your max frequency to the guarantee. But it's not turbo, it's like, well, just limiting the frequency, right? So, you can basically achieve that per CPU by just manipulating the scaling max free. And it's the thing that basically. So, well, ref control has more of that, like with SST, but then it works in a different way because you have like classes of service and you can ask tasks to those classes of service, and then you assign resources per class. Right? So that's a different granularity and a different interface. But again, this is something that has to be done by a privileged and
absolutely.
So now the problem is if we want to have if there is a case for a task to say, hey, I want to get some boost, or I want to background, for example, or something like that.
But depending on how the architecture is implemented, it does or does not make sense to use it as a task attribute. Like say, if it's very slow to take effect, it just does not make sense to make it a task attribute, because then by the time it's effective, the task's already gone.
Because basically, so if there is anything that depends on the task, then it needs to be flagged somehow. So that things can look at that flag and see, oh, this task doesn't need, say, this level of service or that level of service. This is a good class thing in that case, right? But this is done in the hardware or firmware, but that CPPC thing, for example, would require the kernel to be called or like that.
So Peter, it's not always true that the task is already gone. So if you have this one thread from the game engine, the main one, it's flat out. It runs all the time and it's just throttling the CPU. So
for that use case, having a per CPU control which slightly increases the capacity also works, because then the game engine thread is
not always. If you have this magic in the firmware, that's why we are talking about this protocol now. You would like to shift the priority that this CPU running that thread is more important for me. This is what Shuvik was
It's
saying.
literally telling your hardware that whatever happens, you might be under pressure, but this CPU is important. Hit everybody else first. Keep this guy for last. Or if you've got some boost budgets, boost this guy. Right. So it's literally getting above your nominal or then getting hit below nominal at the last moment.
Yeah, exactly.
When everything else has failed.
But then you need to pin your important tasks to that particular CPU, right? Because otherwise,
well,
yeah, I think that's the.
It will go in that direction anyway, because the capacity in the system would drive to the CPU.
Yeah, so
maybe. Hopefully.
So I think the the reason why you would want a per task solution is because you don't have to worry about the double driving, in the sense that you have some user space as a daemon that will configure your priorities, and then your placement will just go completely against that. So a per task solution naturally results in a configuration that's suitable to your tasks. Otherwise, there could be a disconnect or misconfiguration.
I don't understand your point why it would steer towards the priority. We're not changing the capacity, are we?
If they are in different domains.
Boost, like how much boost budget there is not affecting the capacity balance of the CPU, is it?
Well, we should receive the thermal signal for the pressure, so no later you would realize
but
that
it's
the highest capacity.
So
well, we would get that from firmware, how much capacity you have on that CPU.
Well, I'm still seeing this as approaching a problem from a slightly inconvenient side, because we basically have a hardware firmware interface, and we are thinking what it can be useful for, instead of thinking of a use problems we want to address, and then trying to find a hardware firmware interface to address the problem. Because what we started with is basically we have this, more or less complicated zoo of different hardware firmware interfaces that can potentially be used.
So I think the use cases are sort of clear. I think the way that your interface allows you to take advantage of certain functionality, in the sense that you can have sort of generic use cases. That is, it makes sense for the functionality we have today. You need to give priority to boost to important tasks. So that's more or less logical. It's just the different capabilities of your hardware and platform policies can be taken advantage of by using one interface versus the other. So,
question from both.
Yeah, Wolf, but not sure it's what. Last question from Wolf. Hey, Wolf, do you have a question?
Do I have a question? I don't think so. Did I raise my hand?
Oh, yes. Hello, by the way.
Sorry.
That's all right.
So if there are no more questions, I think I had another slide on what would be the non-negotiables, in the sense that basically one of them will be what Peter said, that we have transport constraints depending on the integration, and then what we could do in order for us to at least ensure the sanity of this, not have two things, or the resources driven by two kind of interfaces and not collide with the hard limits that, for example, CPU freak imposes. And I think some food for thought would be what other non-negotiables would be in this space. But I think we're out of time. So thank you very much. Thank you for